This is Jack Jackson. In this video we're going to talk about some calculator shortcuts to finding the symmetric difference quotients. In other words, we're going to talk about how to use a TI84, TI83, TI82, TI-nspire, those calculators to approximate derivatives numerically given the formula. So let's review back here, and from our last video, suppose we had the function f of x equals x to the power 2x, and we wanted to approximate f prime of 3. We're wanting to evaluate this symmetric difference quotient, f of x plus h minus f of x minus h over 2h, for some small h. For example, if h is 0.001, we worked it like this, and this was our calculation. We're doing it at 3, so it's f of 3 plus h minus f of 3 minus h over 2h. And so we can enter like you see here. Okay. Now, let's talk about a couple things we can do to shortcut this process. Let's start by using a TI84 here. Okay, so I have a TI84 emulator. So, one thing that we can do is we could enter our formula in y1. Our formula was, what was our formula? X to the power 2x. Okay, so let's put it in there. X to the power parentheses 2x. Like that. And quit. Now, one thing I want you to notice is that the TI84 calculator has the ability to, or all the TI calculators really, use basically function notation, at least all the graphing calculators. So if I do y1 of a number, I get the output. So for example, if I just wanted to evaluate that function x to the 2x at 3, that would be 3 to the power 2 times 3, 3 to the 6th. Okay? So, of course, 3 to the 6th is 243. We can do that, or 3 to the power, parentheses 2 times 3. In other words, if we want to write it all out, we get that. Now, since I have this in y1, I can do a shortcut. Now, to get y1 at the home screen, here's how you need to do it. Hit Variables, which is this key right here, Variables. We're going to right arrow over to Y variables, select number 1, which is function, and then we're going to select number 1 because I have my formula in y1. And if I say y1 of 3, it's going to take the x value of 3, plug it in the formula in place of x that I have stored in y1, and give me what the output would be, which is 729. Now let me show you a shortcut to that if you have the newer operating system. So the way I showed you just now is what it would look like on a TI83, a TI82, or the older operating system on a TI84. But you can upgrade the operating system on a TI84. By the way, I have a video on how to do that in my algebra videos. Look in the algebra playlist and you can see how to upgrade the operating system on TI84. It should be in that first unit of playlist for algebra. Now, if we take this, if you've got the newer operating system in, there's a shortcut which is alpha F4. And from there you can get it a little more quickly, and now we can say, again, evaluate at 3 or anywhere we want. Okay, now, let's get back to our particular one. We want to do y1 of 3 plus h is 0.001, parentheses, oops, I forgot I need a parentheses around the whole numerator, right? Let's go back and put that in. So I need to insert an open parentheses at the beginning. And then we subtract y1 of 3 minus the 0.001, those parentheses from the numerator, divide by 2 times the 0.001. And this should give me the same number that I got before, which you can see they match. So I'm using the fact that I can store the function in there to put a little bit of a shortcut. Now let me show you a couple things I can do a little bit more of a shortcut. Notice the 3 there is our x value or our a value. So let's just store that in place of x. 3 store as x. And the 0.001 is our h value, so let's store that in place of h. Notice the store key is this one right down here, 1 key above the on key. That gives us the arrow. The h, of course, the letters you have to get by alpha, and then the letters are above the keys in alphabetical order. Except that you can push this button xt theta n, and if you're in y in function graphing mode, y equals mode, when you hit the y equals, y1 equals, y2 equals, then that will be a shortcut to x. So now I can rewrite my difference quotient this way. I can write it as symmetric difference quotient, I should say. y1 of x plus h minus y1 of x minus h and divide by 2h. And that gives you the same thing. Now the beauty of this is if I want to change it to a smaller h, say 0.0001, I can just simply store that as h. So the store button, the alpha button, the power button, which has h above it. So that's 1e negative 4. That means 1 times 10 to the negative 4th power, which is 0.0001. That's what h is at the moment. Now if I do second enter, it'll bring up my previous entry. Do it again, and it'll bring up the one before that. Well, that's the formula I want. This time it will do it with what's currently x, which is still 3, and what's currently in y1, which is our formula, x to the power 2x, and our current value of h, which is now a new value of 0.0001. And we get that, and you notice again, we see these agree for a while, but then they start to disagree slightly after about the second decimal place or so. Okay, and I can do this for even smaller h, 0.00001, let's say, or some other value. That's just the one I happen to choose at the moment. Store that as h, and do second entry a couple times till my appropriate formula comes up, and work that out. Notice these agree at least out to this 8 here. Well, they agree through the 6. They both round off to 0.777, 3059.777. And then here this one has an 8 and this is a 7. So this was good that far. We may have picked up another digit or two there. Let's put in a smaller h, 0.00001. Okay, and let's see what it turns out to be this time. Notice this time they agree. It's only the last digit that's off. So this one here is probably accurate as far as the digits that it shows. We could put in an even smaller one to be sure. And evaluate the symmetric difference quotient, and we get, now look what happened here. We lost some digits. It doesn't mean that those digits are 0. It means that we've started to get so small that when the calculator is doing the approximation in the numerator, that the difference is so small that it's already being rounded off. And when we do the division, this is what it comes out to be, but we lose some digits. This becomes even worse because you might say, okay, well let's do really, really small. Let's take 1 times 10 to the power, say, negative 50. Okay? And store that as h. Boy, this is almost, I mean, that's really close to 0. 10 to the negative 50. Okay? That ought to make a really, really good estimate. And so let's take a look and see what happens. And we get, oh, we get 0. That's not it. That's not close. What's happening here? Well, in this case, this is so small that when it does this subtraction in the numerator becomes 0 as far as the calculator can tell. And so when you divide 0 by something non-zero in the denominator, you get 0. And so what happens is basically the calculator is doing the very thing that that we always tell you not to do, and that is round off your answers in the middle of a calculation. The way the calculator is designed, it can't avoid that. So, in theory, this should give us the best answer yet. In practice, the calculator just didn't handle it correctly. Essentially, it lied. It gave us an incorrect answer. So, what do we need to do? Well, we need to be sure that we go with a small h, but not one too small. And, of course, you can try a few different ones like this to see. Now, let's try basically the same thing very quickly on a TI-nspire. And the TI-nspire basically works the same way, except that the way you get some of the things is slightly different. Okay? Oops. Let's see what I can. Okay. So let's take a look at a TI-nspire. This is what the TI-nspire calculator looks like on the left, and on the right you'll see what a blown up version of the screen. Now this is the home screen, so I could do it completely from the home screen without going to the formula, without going to the y equals basically, by plugging it in. And I could also store some things as x or y. On the calculator here, you want to be a little careful after you're done with this and clear your variables when you're done. Something you don't really have to worry about on the TI-84. So let's say we can again take 3 and store it, that's second variables, store it as x, and these are in alphabetical down here. You just type the letters. You just press the buttons here to type the letters x. And we want to take, again, let's say we take 0.0001 to start with and store that as h. Enter. Oops. Didn't get my h. Oh, no control. Just h. There it is. H. Alright, so we do this. Now what can we do? Well, it is, let's put in the formula, which is x to the power 2 to the x. So we put in, we want to do a symmetric difference quotient. So parentheses around the numerator, parentheses x plus h to the power 2 times parentheses x plus h get out of there, use your arrows to get down where we need to be, subtract parentheses x minus h to the power 2 times x minus h and parentheses around the whole numerator, and divide by parentheses 2 times h. That should give me my same answer that I got a while ago when I used that h of 0.001. Now again, I can change now the h value, or the, well, I'm leaving 3 alone at this point, but I could change the h value and get different approximations here. Now if I want to use the y equals screen, I can do that, but I need to go up here to the little home button, and I want to choose the so use your touchpad here, or clickpad, whatever you have, and choose a graph. It's going to allow us to put in our function here, which is x to the power 2x, and that's f1. So instead of y1, it's f1 of x. And we can hit enter to make sure we enter that. There's what the graph looks like. Oh, that's a kind of a crazy looking graph, isn't it? Okay. But there's the graph of it. Okay, but the point we're looking at is not so crazy. It's over here. Alright, now let's go back now and go to our home screen, just back over here. So use let's see, it's control and left arrow, get you back to the home screen. Now I can enter it this way. It's F1. You can actually just type it in using the letters if you want. F1, like that, of x plus h, or because I have things stored as in here. Okay. You know what? When you do graphing, it may change x, the value of x. So let's go ahead and just put the number 3 plus h minus f1 of 3 minus h and divide by 2h. Get out of there. Divide by parentheses 2 times h. And so you can do it that way. So same kind of a shortcut. Okay, so if you're following along with these notes, if you happen to have my copy of these notes, you can see there is a calculator screen there. There's one there. These are all TI-84 screens showing you how to do this. Here's another example. Okay, actually you try this example now. It's an exercise for you. Here we have a new function, f of x equals 3x squared plus, or times ln of x. Use that function and approximate f prime of 6 using some of these shortcut techniques that we just did. Go ahead and do this now. Press pause and come back when you finish. Press pause now. Okay, hopefully you've worked this. Here's what the answers look like. The screens look like on a TI-84. One way to do it is to put it in y1, put the formula in, 3x squared times ln of x. Then go to the home screen. I used a 0.00001 for h. Store that as h. Do y1 of 6 plus h minus y1 of 6 minus h and divide by 2h, and I get approximately 82.5033405. I tried it with a much smaller h, and at least it agreed out to the 0.5033, so no, it's good that far. Again, we lost some digits because I probably got a little bit too small for the h for us to have any more digits past that. If I start getting smaller h's, I'm going to lose even more digits. So let's try another one. Use the calculator shortcut techniques to approximate f prime at -1, or f of x equals 3x squared minus 4e to the power 3x. Again, you do it, come back and check it. It's very important when you're watching these videos that when I ask you to do a problem, you actually do pause it and try it yourself, because it's only when you really do it yourself that you really start to master this stuff. So I'm trying to put enough examples in here so that you can actually practice some and test them yourself. So please do this. Press pause now. Okay, if you work this on your own, this is what you should have gotten. Here's the TI84 version, and you can see above how we did it. So again, we put the formula in, 3x squared minus 4e to the power 3x. Watch the parentheses there. And again, I used a 0.0001 for h, and this is what I came up with. You might get a slightly different one from different values of h, but if you use a small h, it should work out. Notice that since we have the calculator, it really doesn't matter how small the h is, particularly if we just store it as h, then the rest of the formula types out just the same. Okay, so it really doesn't matter how small of h we use. In practice, we saw already that if you get too small of h, you can actually, it messes up and we just get 0. But if we get something very small but not too small, it does work. Now, let's go on. It turns out that, look at what we have here. On the TI-84, for example, we basically have this formula, y1 of x plus h minus y1 of, let's see, let me get that back again. Here it is. y1 of x plus h minus y1 of x minus h, and then you divide by 2h. So if I go back and forth, you can see the whole formula. Okay, and it says it's 0 for the particular h that we have in now, which is too small. So we put in 0.001 for h, and we're using this particular formula, x to the 2x again. Okay. And let's go back and do the difference quotient again. Let me just see this again, see what x is. X is 3, so this should be approximately f prime of 3 whenever y is x to the power 2x. So f of x is x to the power 2x, and we're going to do f prime at 3. So quit, and let's do, we don't want x, we don't want storing. Let's keep going backwards. Backwards for a time or two. There it is. There's our formula for the symmetric difference quotient, and this is what we get. Now let me show you something you can do here. This is really cool. You're really going to like this. Press the math button and look down at number 8. Actually, before I do this, I'm going to turn this, I'm going to go to mode and turn this, go down here and put math print and turn it off. Go to classic. So if I go to classic, my previous answer will show up on one line, so you can see the formula better in the classic there. And this is what we came up with. Now let's do this. So when I switched it to classic, this will be exactly what it looks like on a TI-82, TI-83, or the older 84s with the older operating system. So you can, or with the newer 84s with it set in classic mode. What you do now is go to math, okay, math, and then go down to number 8, numerical derivative. You put in the formula. Now I have two choices. I can type in the formula, x to the power 2x, and then comma, or if I've already got it in there, I've got this memorized, math 8, shortcut, I can actually put it in as y1, since I've already got it in y1, but if I don't, I can type the formula in there. The second argument you always put in is x. It's always x. That's our variable. And the third thing you put in is the a value, where you want the derivative taken. And the last number you put in is the h value. So this should give me, watch what happens. bada bing, the same thing that we had before. So notice that the numerical derivative, what it's actually doing is a symmetric difference quotient. Let me do one more thing, is if you do this and you leave off the h value, then, I took off too much. You can leave off the h value, but you got to have the x value, the a value. And if you remember, that's exactly what I got with the same thing, but putting an h value of 0.001. So if you leave off the h value, see it is 0.001. Now if I did this and I want a smaller h value, I need to actually put it in, say a smaller value for h. Again, does a symmetric difference quotient with the smaller h value. Now let's see what the same thing looks like in the new notation. Now before I do this, well, let me go ahead and do this, and then I'll maybe explain it a little bit more. So if I tell it to bring up my previous entry, it looks like this. Okay? Now let me just actually go ahead and do it again. Math 8, which is looked like numerical derivative there, but here, this one is the x. The first thing you put in numerical derivative is what goes in this blank here, which was our y1. Try again. The second thing you put in the argument, you put in function or numerical derivative, is the x value, which is always right here, so it's dx. And the last thing you put in is the x value you want to evaluate, what I've been calling the a value, and that is 3. Notice there's no place for the h, so it defaults to an h of 0.001 again. Now let me explain this notation just a little bit more. Okay, so here's another example there using the numerical derivative. Let's do another example here. 5 times ln of x to the power 2 plus x. Put that in as y1. Then go to the home screen, numerical derivative, y1 x 4, because we're doing the derivative at 4, and put in an h. Here I've done it with a couple of different h's, really small h's, and we've got some answers. Now let's do a brief history lesson here. Calculus was actually invented or discovered or developed, depending on your perspective there, over actually a whole number of years. But basically it was mainly invented, if you want to say that, or discovered by Sir Isaac Newton and Gottfried Leibniz. Now why two people? Well, they actually, both of them came up with these ideas, the same ideas pretty much, at almost the same time. And actually Newton came up with his ideas first. He was the first to develop his results in about 1666, but he only published his results a few years later, in 1687, 11 years later, in this massive work called the Principia Mathematica, in which he outlined not only calculus, but also his laws of motion, laws of gravity, how this applies to the planets. So this probably is one of, if not the most important scientific and mathematical works ever written. And Sir Isaac Newton is usually recognized as not only one of the top handful, 2 or 3 or 4 or 5 mathematicians of all times, but also 2 or 3 or 4 top physicists of all times. Certainly one of the most important scientists and mathematicians ever. Gottfried Leibniz also was a very important mathematician as well, but Leibniz actually published his results 3 years before Newton published his, even though Newton actually developed his first. And unfortunately, what happened was there was a bitter argument started to develop over the students of Leibniz and Newton over who was the first to develop this. And it actually created quite a schism between, really the mathematical community of the day, between those who supported Newton and those who supported Leibniz, and particularly the British mathematicians kind of split off from the rest of Europe, and we had a big schism for a long time, which is kind of unfortunate. As it turns out, historians now believe that both of these great mathematicians developed these ideas on their own, independent of each other. But because of that, we have developed different notations for the derivative, and we still keep and use both notations because they're both useful. Now, when we say f prime of a is the derivative function f at the point x equals a, that notation is due to Newton. So that's Newtonian or Newton notation. So if you do the same thing in Leibniz notation, there's a couple ways you could write it. You could write it as df over dx such that the vertical line x equals a, or d over dx of f such that x equals a. So a little bit more cumbersome notation for this particular thing on the Leibniz side. The Newton side, it's a little bit more compact. So here is probably preferable in a way to use the Newton's notation. So you might wonder, well, why do we keep the Leibniz notation? Well, there's several ways we might do it. One of the reasons why Leibniz notation is nice is the df over dx is actually suggestive of the actual definition. So remember, the derivative df over dx is the limit of delta f over delta x as the delta x approaches 0. Of course, delta f also approaches 0. And so f prime of a, being df over dx evaluated at x equals a, is the limit as delta x approaches 0 of delta f over delta x, if we want to simplify that. So one of the ways you can think of it is the df as being an infinitely small change in f. So the df is what happens to the delta f when you take the limit, and the dx is an infinitely small change in x. It's what the delta x does as you take the limit. Well, this is not really exactly formal language. This is kind of a fuzzy way of saying this, and because of this type of language, this was used by some of the founders of calculus, this led into some problems with making it rigorous enough. So later it was deemed that was an insufficiently rigorous way to think of it, and so that's when they came along with the delta and epsilon definition of limits to make these concepts more rigorous and make them, make the foundation of calculus firm. But nevertheless, it's somewhat suggestive here in the notation, and it's another way of looking at it that's helpful. We're also going to think of d over dx as what's called a differential operator. It means take the derivative of f and evaluate that at x equals a. We'll talk more about that interpretation a little bit. But why I wanted to say that at this point is that is exactly what the newer notation looks like on the calculator. It looks like Leibniz notation. In fact, it's really a better notation than just to say in derivative. This is an actual derivative. Take the derivative here, d over dx of the function y1 evaluated at x equals 3. This is Leibniz notation. Of course, it's not actually doing the derivative on the calculator. It's actually doing a symmetric difference quotient, as we saw, and specifically it's using an h of 0.001. And so that's usually good to several different decimal places, not necessarily all the way out on the calculator. Now, what about on the TI-nspire? Okay, well, you can do the same thing on the TI-nspire. Okay, so here is the TI-nspire calculator. Okay, and we can get the same thing. Now, the way to get the derivative here is from this symbol palette. Can you see it right here? There's this key that looks like a book that's for the catalog, and right next to it there's this thing with some symbols on it. Click that, and we get our list of symbols here. Use your cursor to choose the right one. And you can see the one that highlighted, that's the right one. That's the one that looks like the Leibniz notation for the derivative. Click on that, and fill in the blanks. This one's always x because we're taking our, this basically is just telling us x is our variable. And as long as we write our formula here in terms of x, we have it. Now, here we want to write our formula. Let's see which one I wanted to try. Let's say 5 times ln of x to the power 2 plus x. Let's do that one. Okay. 5 times, oh my, can I remember it? I think it was ln of x to the power 2 plus x. Was that it? Let me go back to 5 times ln of x to the power 2 plus x. Yeah, that looks like it. And now we wanted to evaluate it at what value? F prime of 4. So now we need a such that. Now such that's a vertical line. You can see it right here. So that's in blue. So we do control equals, and then we select it from this list, such that, and then we say x equals 4. So that's the Leibniz notation there for the derivative. Evaluated x equals 4, and there we go. Alright, so that's the way we do it on the TI-nspire. So it looks like just like the newer notation on the TI84, you just get it a little bit differently. Now, what I want to show you now, though, is if you actually had a TI-nspire cast version, something even cooler happens if we do the same thing. So choose, I'm going to enter exactly the same thing. This is a TI-nspire cast. Okay, and let's see if I can remember what it was. 5 times ln of x to the power 2 plus x. Okay. Oh my, we have a w there. I should have had an x. Okay, that looks good. Alright, now we need to such that. Control equals. Notice that the layout on the keyboard and everything are exactly the same on the nspire cast or the nspire non-cast. And okay, but look what happens on the cast version. This is actually the exact answer. 5 times parentheses 4 ln of 2 plus 3 all divided by 2. That is the exact answer for this problem. So the cast version knows how to apply some shortcuts, algebraic shortcuts that we'll learn later, and work out this exactly. Now if I just tell it to take that answer now and do control enter, that'll give me approximately what that is, which is what we got on the, see if you remember, that's what we got when we entered that on the non-cast version. So there's the whoops. There's the non-cast version, 14 point da 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 da. Okay, and then the cast version, same answer, or at least should be very close. Actually, this one's going to be more accurate because it actually does an exact value and then approximates that. But they should agree to many decimal places. Let's see if I can make that. We can see both of them. 14.431471805. They're both accurate to all the places. So they both work all the way. And so there is you can actually get an exact value from a CAST calculator. CAST stands for Computer Algebra System. And so there is how you can use your calculator to get a very nice and easy actually shortcut to finding a numerical derivative. Well, what is a numerical derivative really? It's a symmetric difference quotient. That's what your calculator is actually doing.